All right. So thanks, Lorenz Eberhardt, for giving this very nice, agreeing to giving this very nice second talk. I'm going to give you another introduction. So Lorenz Eberhardt is a theoretical physicist working on string theory and quantum gravity. His research focuses on dualities, meaning unexpected equivalences between different physical descriptions, and on developing methods for exact computations in quantum gravity. His work includes an exact solution of three-dimensional quantum gravity with negative cosmological constant, applications of analytic number theory to string amplitude computations, and a direct proof of the ADS3 CFT2 correspondence. He is an assistant professor at the University of Amsterdam, and after a long postdoc position at the Institute of Advanced Study in Princeton, he earned his PhD at ETH in Zurich in 2019. So please take it away, Lorenz.
Thanks a lot for the invitation. And today is roughly the continuation of what I told you last week. And I want to talk again about string amplitudes. And so I started this endeavor roughly 5 years ago, mostly with Sebastian Mizera. In the meantime, various other people joined in for the fun. So I want to emphasize my student, Marco Baccianti, and also Cornell group at Cornell, Tom Hartman and Chandra. Very good. So I start somewhat slowly, and there's going to be a slight repeat from last week since I didn't know whether there will be new people. So apologies if it's a bit boring in the beginning. But let's start again. And I like this comic. This is the usual reaction that you get when talking to non-string theorists about string theory. So I want to change that a little bit. So hopefully we already changed it last week a little bit. But let's tell you a little bit more. All right, so string theory aims to describe nature at all scales. And so it reduces to ordinary quantum field theory in a low energy limit. But in string theory, we can also ask questions about the high energy limit. That's mostly what I want to do today. And I sort of have in my head this picture. If there's some very advanced future civilization, they could, in principle, build a collider that is very big, so let's say solar system size, and they find some technology to prepare gravitational waves as initial states. And they decide to smash those gravitational waves into each other at very high energies, and they produce all sorts of things in there, just like what we do at LHC. Like black holes or Higgs bosons, or whatever your favorite particles are. And then they measure, again, some gravitational waves or other particles that come out of the process. So this is a particular S-matrix element. And of course, such a grand agency doesn't currently exist that would agree to such a collider, but we can ask the theoretical question, what happens to the amplitudes? So string theory makes predictions within that theory about the scattering of gravitational waves or other particles. And for me, at least, the main problem is these predictions are in principle there, but it's just very, very difficult to compute them. It's essentially as difficult or harder than perturbative quantum field theory. And you probably know that in quantum field theory, you can do one-loop computation, two-loop computation, and then at some point you go to three-loop computation, it becomes really hard. And then if you're very strong, maybe you can put it on some supercomputer and do some non-perturbative computations. But it's just a technical obstacle. So it's the same as saying QCD tells you what the mass of the proton is, but good luck computing it. So we saw this amplitude last time. This is the tree-level amplitude in string scattering for string scattering. So it's a famous Virasoro-Shapiro amplitude. And it's this very nice function of STU. I told you some nice properties about it. I'll review them in a second. And in perturbative string theory, the way we compute amplitudes is just the same way as what we do in Q of T. So we have some perturbative diagrams corresponding to Feynman diagrams, and they describe these processes of the string. So the string comes in, there are these tubes, so they carve out these tubes in space-time, and they can interact in some way, and they go out again. And then you have more suppressed processes that are at high loop order. And so also this I told you last time, but let me just recall. that these diagrams, contrary to field theory, so this reduces to field theory in the IR. So everything that you know about field theory in the IR is still true in string theory, but in the UV it differs drastically. So in particular, these diagrams are UV finite, essentially because the string length, so the characteristic size of the string is built in as a fundamental scale. Another stark difference is that in field theory, we typically have a proliferation of diagrams. If you go to higher loop orders, you get many, many diagrams. Whereas in string theory, you just have a single diagram at every loop order. So string theory unifies all the different field theory diagrams to one diagram. Because recall, this still reduces to field theory in the low energy limit. All right, so let's go back to our tree-level contribution. And it was this function. There's some polarization structure in front because we're scattering gravitons, so this will depend on polarizations. I just put them in this tensor, and you don't need to worry about how this tensor looks like. There's some contractions of different polarizations. Yep.
Sorry, just a question on the last slide. I was just thinking about the one diagram per loop order. Is there some kind of intuition to think about that? And then also how do I think about this one diagram turning into multiple diagrams if I were to lower the energy scale?
Very good. Yes. So the intuition is essentially, so first of all, there's one diagram because you can only draw one surface, smooth surface with a given number of holes. It's just a unique surface at every loop order topologically. But to your question, how it reduces to field theory, essentially it reduces to field theory if you make different parts of the diagram long. So you might decide, for example, to make this propagator long here, so very long and thin, so that at the moment it looks kind of thick. And maybe you make this part long, and then these become legs in the field theory. Essentially, if you deform the shape of the surface such that it looks approximately like a Feynman diagram, just slightly thickened. And you can imagine you can make different Feynman diagrams, right? You can make the one where you have like the double box, or you can make one where instead of a box here, you have only a triangle by degenerating the surface in different ways.
Okay.
So in some sense, all the boundaries of moduli space of like that parameterize the different shapes of the surface, all the boundaries correspond to the field theory diagrams.
Okay, thank you. That makes sense.
Very good. Yes, so this, and I mentioned also these things last time, but let me review them. So this tree-level amplitude is manifestly crossing symmetric, so an ST and U, meaning that you can take out an outgoing particle and exchange it with an ingoing particle. This requires you to analytically continue the amplitude in ST and U. It is also Regge bounded, so meaning that if you go to high energies at fixed momentum transfer, then this amplitude doesn't grow too fast. It grows only like S squared. And the square is because it's a scattering amplitude of gravitons, and they have spin 2. So the 2 is, the square is because of spin 2. So this is expected from general S matrix scattering theory. And maybe most excitingly is that the amplitude is UV soft, in the sense that if you take the energy very large and you keep the angle fixed between the incoming and the outgoing states, then in field theory, the amplitude typically grows, or it's polynomial. It's typically something like 1 over S plus 1 over T plus 1 over U. Whereas here, the amplitude exponentially dies off. And I think there was so that's sort of the characteristic thing compared to field theory. In field theory, you're not even supposed to ask this question necessarily, what happens in UV. But in string theory, it just exponentially dies off. So that's completely different UV behavior than field theory. And finally, the amplitude, of course, is consistent with unitarity. And the slightly historically amusing thing is that imposing these properties is actually very constraining. And so people in the 60, they asked, can we write down a function of ST and U that satisfies all these properties? And they come up with this function. And well, even before there was one that corresponds to the open string, that's the Veneziano amplitude. And then later string theory was developed and was actually realized that this is the scattering amplitude of string theory at tree level. So that's quite amazing. It tells you how constraining these properties really are. So we want to know what happens at higher loops. And at higher loops, unfortunately, there's not such an explicit formula. So ideally, of course, we want to know even what happens non-perturbatively with the amplitude, but that's a hard question. Very good. So instead of, so computing them explicitly is hard, but we still want to know what the properties are. Especially we're interested in this high energy regime because this is where our future civilization built their collider and is expecting to see maybe black holes in the scattering process. Just like people were worried about 20 years ago, we would see black holes in LHC. It's maybe not that far off. Very good. So to give you a small preview, so what we will be able to compute is basically a one-loop amplitude in string theory. And if you study field theory, this might sound ridiculous to you because in field theory, doing one-loop amplitude is not that hard. It typically is some kind of logarithm, dilogarithm, some kind of special function, but it's not that terrible. Whereas in string theory, already the one-loop amplitude is quite hard. And the main thing I want to emphasize already at the beginning, so here, you see on the x-axis the energy, on the y-axis the amplitude. Notice it's a logarithmic scale. And I plotted the absolute value of the amplitude. So the spikes here are just zeros of the amplitude. And I plotted the imaginary part and the real part separately. And I also multiply by the sine squared factor. It's just because the amplitude has poles whenever one of the intermediate particles goes on shell. And it actually has double poles at one loop. That's why I just multiply by the sine squared pi s to cancel all the poles and get a nice plot, essentially. And the main thing that you see is that this amplitude has various oscillations and it exponentially decays. So this is, and low energies, this is where you get field theory. So in field theory, you have this somewhat boring part of the amplitude. And at very high energies, you're going to have this exponential decay, just like you have at tree level. Very good. So I will come back to this plot.
I'm sorry, maybe just a quick question.
Yep.
So there's clear structure there, which is saying, and it's as a function of S, which tells me that there's some kind of a scale. So what is that scale and what's the physical interpretation of that scale? Thank you.
Yeah, thanks. The scale is the string scale. So it's the characteristic size of the string. And that scale, another way to think about it is the tension of the string. The string has some tension, which is dimension 4. And it sets, for example, the masses. And in fact, this is this parameter alpha prime. So I put alpha prime to some number. This is my unit. And it sets the masses of the massive strings states. So there's the massless states, but then you have massive states. In my convention, the mass squares are exactly integers. So that's what sets the scale. You can ask, how does that scale compare with the Planck scale? So the string scale and the Planck scale are not the same thing, because also you have one dimension less constant in the game. If I just go back here, which was the string coupling constant. So combination of the string coupling constant and that string scale becomes the Planck scale. In fact, if you would do this computation in gravity, then because this is like, let's say, an exchange diagram, it's a tree-level diagram, it will come with 1 over g Newton, and this one will come with 1 over g Newton squared, 1 over g Newton cubed, and so on. So you see that g Newton is proportional to, gs is proportional to 1 over g Newton to the 1/2. And then you need to put the appropriate power of alpha prime to make the dimensions work. All right.
Hopefully great, thank you very much. That was really nice.
Okay. Yeah, and you see also the scale appearing here. Very good. Yes, so you can also do this same thing for the open string, which is scattering of gauge bosons, and basically qualitatively looks the same. All right. So for the rest of the talk, I'm going to go back essentially what we did last week and continue where we left off. So we'll learn more about string amplitudes. And then I'll tell you a particular method that we use to evaluate the one-loop amplitudes. And finally, we go to the high energy limit, which is also known as gross limit, Mende limit. By the way, in the abstract, I told you that I will talk about it in the other order, but I decided that this is maybe clear. All right, so let's review what we did. So in quantum field theory, we can write amplitudes as integrals over Schwinger parameters. And you can view Schwinger parameters as the proper lengths of Feynman diagrams. And so we saw that we can view QFT as a theory of 1D quantum gravity because we're integrating over all possible diagrams and over all possible metrics on these diagrams. And so this is a integral over all 1D manifold with certain singularities. And what you do at the singularities are basically the Feynman rules. They tell you how to treat singularities. In string theory, we replace these 1D diagrams by 2D surfaces. So we get this worldsheet scattering. And so string theory you can think about as a 2D theory of quantum gravity on the worldsheet. And it's not necessary to introduce any singularities here. It's a completely smooth worldsheet. And so in string theory, the amplitudes are expressed as integrals over all possible 2D surfaces of some integrand. And I told you that there's a miracle that happens is that the integrand turns out to have an extra symmetry, which is y-symmetry, where you can sort of scale in, zoom into the surface or zoom out. And gauging it allows you to reduce this integral. This integral becomes a finite dimensional integral. And there's a danger with gauging the y-symmetry because it can be anomalous. And it is exactly non-anomalous in 10 target space dimensions. That's where the 10 dimensions of string theory come from. All right. So hopefully that rings a bell from last week. So now this is new things. I told you everything that was true in QFT is still true in string theory in the IR. So in particular, in QFT, you need to worry about causality, correctly implementing causality, which is the I epsilon prescription. It tells you how to avoid poles when you do loop integrals. And so there was nothing to be seen of this so far in string theory. So I'll tell you what the manifestation is, and this will be quite important for us, is that actually there's a slight refinement of this formula that I showed you. So the amplitude in a given loop order G and some number of external particles N is an integral over this modular space of surfaces. However, this modular space of surfaces describes Euclidean metrics on the worldsheet. But these amplitudes are really Lorentzian objects. So actually what you want are Lorentzian metrics on this worldsheet. So if you think about it a little bit, if you have one of these worldsheets, it's actually not possible to globally put the Lorentzian metric on such a worldsheet. So instead what you need to do is you need to first complexify this space. So then you go to the space of, say, complex metrics on the worldsheet. So they're neither Euclidean nor Lorentzian necessarily. And then you pick some contour, so some half-dimensional submanifold of this space that you're integrating over. And it's a contour that is consistent with Lorentzian space-time. So essentially the contour looks is the same as the original integration contour whenever you're sort of far away from boundaries of modular space. Well, if you tend to one of the boundaries, well, then you reduce to field theory. And in field theory, you know that the proper times, the Schwinger parameters, they need to be Lorentzian. So you have a Lorentzian proper time on the world line. And that means that you have to do a Wick rotation, and this contour turns into a complex plane. I'll tell you examples in a moment, if that sounds a bit abstract. So it's a bit surprising that in the grand scheme of things, this was only discussed about 12, 13 years ago. So let me tell you the simplest example, which is the open tree-level amplitude. So last time we discussed the closed tree-level amplitude, but it's a bit hard to draw this contour for the closed case, so apologies. So we're discussing now the open case. But so this is the 2-to-2 scattering amplitude of open strings, meaning that the worldsheet topology is a disk where you can view 1 and 2 as the incoming strings and 3 and 4 as the outgoing strings. And it's again an integral that is very similar if you look back to the closed string integral. The only difference is that it's a real one-dimensional integral, whereas the closed string was a two-dimensional integral. It was a surface integral. And the integrand is essentially the same, except that there's no mod squared. If you read any textbook in string theory, they typically tell you that this integral goes from 0 to 1, which corresponds to essentially integrating. So there's one invariant quantity of these 4 points, which is called the cross ratio. This is this z. And you need to integrate over all possible shapes, which you can think of as integrating, say, the first vertex operator from the place where it hits the fourth one up to the place where it hits the second one. And so it's an integral from 0 to 1. And you can think of this z parameter as being e to the minus tau, where tau is the Euclidean Schwinger parameter. And now the point is that if you go close to 0, well, then you should Wick rotate the Schwinger parameter, which means in terms of z that you're not going all the way to 0, but before you hit 0, you turn into the complex plane and you go around the origin. So if you replace tau by I tau, that will describe a circle. And the same happens near the other boundary of the integral. Again, to come back to the previous question, in field theory, this region of the integral will correspond to an exchange diagram. So it's a cubic theory. This corresponds to the exchange diagram in a T-channel, and this one corresponds to the contact diagram, where you have a quartic interaction. And the point of doing this epsilon prescription is that now this integral is actually convergent, whereas before you see, because if you write z to the minus s, and you make s positive, then this integral will blow up near z to 0. But this contour avoids that dangerous point. And now you traded a divergent integral for an oscillatory integral. But that's very typical in QFT also. Okay, let me also tell you a more complicated example. If you do the one loop integral, then now you will have 4 Schwinger parameters. Just like you had 4 Schwinger parameters in QFT, you also have 4 Schwinger parameters in string theory. And in the open string case, so this modular space of open strings, one loop and 4 punctures is 4-dimensional, corresponding to the 4 Schwinger parameters. And the integrand is some very classic functions. So this is this Jacobi theta function. So Jacobi knew about this 250 years ago. This is some nice functions that you can define on the annulus or the torus. So yeah, maybe I should have said the topology at one loop is an annulus or a cylinder. And again, there's some question what you need to integrate over. I will mostly focus on the part in tau. And it turns out the correct contour that is consistent with causality to integrate over is the contour that goes from 0 to 1/2 in this tau parameter. Details are not super important. I just want you to know there's some appropriate contour. You can do the same thing with the closed string. So for closed string, we're talking about graviton scattering. Again, there's some integrand. For closed string, the integral is always twice as many variables. So it's an 8-dimensional integral. And in this case, you need to integrate over some region in tau. Tau, again, you can think of these as being roughly the 4 Schwinger parameters. Tau, you should think of as the total length of the torus, the imaginary part of tau, and the real part of tau is the twist of the torus. Because I should have said maybe, again, the one loop diagram in closed string theory is a torus. And then you get some integrand, and this integrand is essentially the Green's function of the torus. So this formula was written down a long time ago by Green and Schwartz. And again, this integral will be, if you integrate like this, it will be divergent because you're not taking care of the correct causality implementation. So to correctly do it, you have to integrate over some region here, over these tori. And then before you hit the boundary of this integral, this is where the torus becomes very, very long, and you're essentially talking about approximately field theory. This is where, again, the integrand reduces to field theory amplitudes. You need to turn into a complex plane. So in practice, you sort of call the imaginary part of tau, you call it y, and then you deform this contour in y, and it goes in the imaginary direction of y.
Sorry, can I ask a question?
Yep.
So I'm just thinking about this contour. So your contour, it represents a torus in this case, right?
Mm-hmm.
And I'm just wondering, it doesn't seem like it's a closed contour, or is that just like, I'm just thinking about integrating over the red line, the thick red line.
Sorry, it's the interior of this.
Okay, I see. And does it extend out to infinity, or?
It extends all the way up to infinity, indeed. And this modular space has a cusp there. So it's strictly speaking not compact. But it's just the same as in field theory. So you see this integral also goes all the way up to infinity. So you can literally think of the imaginary part of this red part as one of these L's. So it also is integrated all the way up to infinity. Notably, to make one point I mentioned earlier, here this integral goes all the way down to 0, and this is where the UV divergences come from. And if you go to the string theory case, it does not go all the way down to 0. So this is where the UV divergences would live, and it's just not part of the integral.
Okay.
Great. Any other questions I should ask? Hopefully this is not too much information dump. But yeah, so these are these sort of the integrals made explicit that I told you last time over these various spaces. All right, so in some sense, at this point in the talk, we're just talking about an integral. So most physicists spend a lot of time computing integrals in their careers. So we want to know how this integral behaves. And the question is how to evaluate it. So if you're a naive person like me, then you would say, well, just put it in a computer, do some Monte Carlo sampling and see how it looks like. This doesn't really work very well. The reason is because it's a very oscillatory integral. So there's going to be a huge amount of cancellation. And numerically, this is really terrible, this integral. So you cannot really put it in a computer. Whereas mathematically, it's a convergent representation of the amplitude. So what we're going to do is to use contour deformations. So we all like complex analysis. In complex analysis, when we compute integrals, we can deform the contour. So in particular, one thing I should have maybe said is that in this contour, where I turn into a complex plane, I made some choice where I turn into a complex plane at some height. I can deform this height smoothly. This is a contour deformation. It does not change the result. Very good. So let's play with contours. So a simple thing that you can do is to compute the imaginary part of the one loop amplitude. And just like in QFT, there's an optical theorem, string theory, and it tells you that the imaginary part of one loop amplitude is related to a square of tree-level amplitudes. So you would expect that the imaginary part is much easier to compute than the full amplitude. And indeed, I'll tell you how that happens. Because the imaginary part you can compute by taking one side a sign of the I epsilon prescription, where you turn sort of out of the slide, and subtract from it the other sign of the I epsilon prescription, where you go into the slide. And if you take the difference, well, this part of the contour is going to cancel this part, this Euclidean part of the contour, if you want. And you only retain the fully Lorentzian thing that now just goes into the slide. And so I'll claim this is much simpler to compute than this thing. And the reason is that, again, I can do contour deformation. So I can push this thing up to infinity as much as I want. If I push it up to infinity, well, the whole thing is going to reduce to field theory, essentially. And on a more technical level, I can compute the integral over this red contour. Again, it's a two-dimensional contour, by knowing the behavior of the integrand near this cusp, near the region where the imaginary part of tau goes to infinity. Because everything in the integrand that dies off as you go to infinity will not contribute to this integral, because you can just make it disappear by pushing up the contour. And that's the reason why this is kind of simple to compute. I didn't put the final formula, but what this leads to is that the imaginary part is given by unitarity cuts of the tree-level amplitudes. And all these parts that blow up here correspond to the possible intermediate states that are kinematically allowed in the scattering amplitude. Okay, so that's a slight warm-up to these contour deformations. Maybe I should ask first for questions. There we go. Further, everything crystal clear. Very good, hopefully. Please. Okay. But yeah, so that was sort of relatively easy, and it was expected to be easy. The real part is much more challenging, so that's a genuine new thing at one loop. And what we use is some trick from math that's called the Rademacher expansion. And the fundamental idea is still we're doing complex analysis. We need to integrate over some contour, and we can try to deform the contour in a useful way. And we'll try to deform it in such a way that we can compute the integral without actually doing the integral, in the sense that we deform the contour such that the answer is only sensitive to the behavior of the integrand near the cusp in moduli space. So this is what we did for the imaginary part. We, if I just go back, for the imaginary part, the contour was this, and we can deform it, and deforming in this case just means take it to infinity, such that the answer only depends on all the singular parts of the integrand near the cusp that lives up here. Okay, so the idea is the same, but of course it shouldn't be very clear to you how to deform this contour or some two-dimensional contour. It's kind of hard to think about. So I'll tell you first the open string case, which is a classic number theory. And so remember that the contour was this one. It goes from 0 to 1/2. This is the contour for the open string at one loop. And I drew all these funny circles here. So those are known as Ford circles. And they touch the real line at fractional values. And the radius of this circle is 1 over the denominator squared over 2. So in any case, they form this nice pattern that they all touch but never overlap. And why are they useful? Well, they're useful because you can deform the contour successively. And in some step n of this contour deformation, you follow all the circles whose denominator is at most n. So concretely, for example, in the fifth step, when you deform this contour, you follow the circle. So there's a big circle here that I didn't draw that touches 0. So you follow first this circle until you go to the 1/5 circle. You go around this 1/5 circle to the 1/4 circle, around the 1/4 circle, around the 1/3 circle, the 2/5 circle, and the 1/2 circle. Okay, and you keep going like this. So obviously this is a contour deformation. It shouldn't be clear to you at all why you should do this contour deformation. But let's just roll with it and continue and deform the contour more and more and more. And cross our fingers. If we cross our fingers a lot, then we see that in the limit, where we take this procedure to infinity, our contour goes around every circle here, every circle touching every rational number between 0 and 1/2 exactly once. So you can already see here, it almost goes around the whole 1/2 circle, and it will go more and more and more around it if we go also towards these smaller circles. So provided this whole thing converges, it tells you that the initial integral over this contour can be rewritten as an infinite sum over contours that go around these circles. Now, the main point again is that it's easy to compute the integrals around the circles because, well, you can again deform the circles if you want. You can make them as small as possible. And once you made them as small as possible, they will only be sensitive to the singular behavior of the integrand near these rational numbers. So computing them is as hard as computing the imaginary part, which was easy. So in some sense, the real part, to compute it just recycles the imaginary part computation infinitely many times. You can do the same. I'll get to explicit results in a moment, but I want to mostly talk about the closed string because it's a bit more well-known, a bit cleaner. And there's a similar story for the closed string, that you can compute an integral over this funny contour by deforming the contour in both tau and tau bar. So you basically need to analytically continue this thing to the where tau and tau bar are independent. And you can write it as an infinite sum over all the cusps in moduli space. And again, there are infinitely many as on the previous slide. And then the important thing is that there's a holomorphically split integral. So it's an integral over tau and over tau bar. And the integral over tau goes over some horizontal contour. And over tau bar goes over these circles. And both of those are again easy to compute because you can take the contour over tau and push it all the way to infinity. So the answer will be only sensitive to the singular terms in the integral. And similarly in tau bar, you have to integrate over a circle, and you can make the circle as small as possible. And the answer is only sensitive to the singular behavior near these rational numbers. You see there's also some number theory stuff going on. So there's some extra factor, and this extra factor involves the so-called Dedekind sum. This is some sum over fractional parts of rational numbers. These are some numbers. You don't have to care about it at the moment. But so to prove this, it goes through a lot of number theory. Very good. So this is a general formula that you can apply to whatever problem you want if you encounter an integral like this in the wild. So let me tell you first a simpler application before we go to full string amplitude is if you compute a one-loop partition function in string theory. Well, then this one-loop partition function, so 0-point scattering amplitude if you want, it computes just a shift in the cosmological constant. It computes the vacuum energy or the Casimir energy of the target space. And so it's some explicit integral, again involving some of these Jacobi theta functions. Of course, you can do this integral numerically here. It's not particularly hard, but I just want to emphasize the numerical this method. And this formula on the previous slide rewrites this integral as an infinite sum. And this infinite sum, again, is the sum over all these cusps. So this parameterizes all rational numbers, where you sum over A over C, and A and C have to be coprime. And I told you that you can do these integrals here analytically, and they turn out to be these Bessel functions. And again, you have this number theoretic things going on. So this is a rapidly convergent representation of this integral. And what is perhaps interesting about the result physically, except for this being toy example, is that the answer is positive. So you get a positive cosmological constant at one loop in this theory. And this is some particular string theory. It's a non-supersymmetric string theory in 10 dimensions. So if you have heard that there's only supersymmetric string theories, I'm afraid you've been lied to. Anyway, very good. So let's go to or are there any questions? Okay. Then let's go to the full amplitude. You can play the same game with any of these integrals. So you can play the game also for the full amplitude. Again, you can turn the integral into a sum, and the sum now runs over all the boundaries of this modular space M14. So there's a sum over rational numbers between 0 and 1. This we already saw. There's also integrals over this Z, the locations of these vertex operators, basically the other three Schwinger parameters that I haven't talked about. They lead to more sums. So there's a big sum, and then there's a piece, sort of a building block piece. And this you can evaluate in closed form. And it looks essentially as complicated as the imaginary part. So it's some kind of unitarity cut with additional phases, essentially. The main point is that this formula, it looks kind of complicated, it still has infinite sum and so on, but it makes almost all the analytic properties of this amplitude completely manifest. And it also avoids all this large cancellation that you had in the integral representation. It's not present in this formula. So it's actually a useful formula to explore the amplitude. So again, yeah, it's a convergent representation of the amplitude. And it's for some range of energies, it's very practical, this formula. And this range of energies is sort of intermediate. Let me tell you why. So it's hard to take a low energy limit. So this is when you take S to 0, then everything reduces to field theory. So if you thought that this is going to be useful for field theory, then unfortunately this formula exactly breaks down if you try to take the field theory limit. So it's a inherently stringy formula, essentially because the convergence breaks down of this infinite sum. So that's a bit weird, maybe. It's not really a big problem because when S is small, we're basically talking about field theory, and there we know how the amplitude behaves. So it's essentially, it behaves like a QFT amplitude. So it's not a big problem, but it's a bit annoying that we can't simply make contact with QFT. Similarly, it's also kind of hard to go to very high energies, very, very high energies. And the reason is just that the unitarity cuts become more and more complicated. So if you do a unitarity cut, you have to sum over all intermediate particles, so all possible masses and all possible polarizations. And it's just if you go to higher and higher energies, there are more and more possible internal states that you can put and more polarizations you have to sum over. So that becomes more and more complicated. So in practice, depending what quantity we're exactly computing, we can go for the full amplitude roughly to order 10. If you compute other things like mass shifts, we can go much higher. All right, so that's essentially the situation that now we have access to the amplitude intermediate regime. We have access to it at small regime because this is where it's field theory. And then I'll tell you later how to get to very high energies. So we can sort of cover the whole regime. But let's first look at some plots. So these are some of the plots I've showed you at the beginning. This is a slightly different one. So if you just implement this and you plot the result, here plotted the answer as a function of S, the energy, but I kept the momentum transfer to be 0. So this is the total production at one loop. And you plot the answer. Again, I multiply by the sine squared pi s to cancel the poles. I also multiply by s so that it's a nicer plot. Then for this, the asymptotics are actually known because you're talking about this Regge limit that we also already mentioned at tree level. And it's this dashed line, the asymptotics. So that's known to be correct. What's a bit, and it's purely imaginary also. So this yellow curve must die off for very large values, and the blue curve must approach this dashed curve. So what you see is that essentially it's terrible. It doesn't match very well. Even though it's technically correct that this is the asymptotic, the error is, we know the error is of order 1 over log s, which means essentially that at any reasonable energy scale, this is a terrible approximation, this dashed line. So we can compute corrections and so on, but essentially, yeah, you shouldn't really use this formula of the asymptotics. Nonetheless, this formula is consistent with the expectation from Regge physics. So it was discussed, so this asymptotic formula was discussed by Amati, Sciafaloni, Veneziano, and Sundborg many years ago. You see also these very thin lines here. This is what you get from field theory. So you see it's a decent approximation for very low energies, but pretty quickly breaks down. At the latest, when you approach this energy 1, this is where you have the first massive state in string theory. Should also say maybe there's all these dashed lines. If you look very closely, the dashed lines is where the amplitude has thresholds, because if you increase the energy, you can excite more and more, or you can produce internal states that are massive. And whenever you cross one of these dashed lines, there's a new internal state you can put. And it manifests itself as a discontinuity in the amplitude. So maybe you can see the amplitude looks reasonably smooth, but it has branch cuts at all these dashed lines. All right, so that is actually kind of similar to field theory, but now if you go to fixed angle, so this is a similar plot as on the previous slide, but instead of keeping the momentum transfer fixed, I keep the angle fixed. So I have some incoming gravitons and some outgoing, and I'm measuring in the detector at some fixed angle. And then the amplitude looks completely different. So now it's a logarithmic scale, so it dies off exponentially. This is the plot that I showed you in the very beginning. So hopefully now you understand a little bit more. This blue curve is produced by just taking unitarity cut. That's why it's a very smooth curve, because it's easier. Then this yellow curve is done by doing this Rademacher expansion type of logic. You see it breaks down for small energies. This is where the numerics gets sort of bad. You also see again these thin lines. This is the field theory prediction. And again, it's kind of good for very small energies, but quickly breaks down. Okay, so I think I explained you everything except for this dashed line. So there's also a prediction for high energy, which is by Gross and Mende. And what you already observe is also that this prediction seems to be terrible in the sense that, okay, very roughly it matches, that it exponentially falls off, but it doesn't, and again, it's purely imaginary. Whereas the data does not seem to suggest that the answer is necessarily purely imaginary, or that you get this smooth line.
Sorry, can I ask another question? So for both this plot and the previous plot, you have this dashed line, which is like these predictions. So what's your sense in what these predictions, where do those predictions come from, and why is your model different from those predictions, and what is what's the correct model, I would say, why does it differ?
Very good. I'll answer the Gross-Mende in a couple of slides. So let me answer your question for the Regge asymptotic. So they have two sort of different answers slightly. So in principle, this is a prediction that comes from S-matrix scattering. So in S-matrix, you know, the S-matrix has to be unitary, causal, blah, 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 all that kind of things. And you can derive from this how it behaves for large energies. So this is known as this Regge limit. And you basically find that it goes to, in perturbation theory, it goes like S cubed. Let me not tell you the precise answer, but you find some answer. And then there's a sort of second approach, is that just you take this integral that I started with and you try to evaluate it for very large S, but analytically. As I'll discuss in a moment, you can do this integral in saddle point approximation. And for this Regge limit, it was actually shown that both methods give you the same answer, which is this dashed line. So here we know for sure that it's correct. I'll tell you the problem with this cross-Mende limit in a moment. That's okay.
Okay. Thanks.
Very good. Also, I should mention, if you want to play around with this, all our code and data is on the internet, so feel free to use them. Very good. So let me talk about this cross-Mende limit, unless there are other questions. Very good. So let me answer the question. So where is this prediction coming from? Well, it's coming from the integral. So at very high energies, the string amplitudes are supposed to simplify in the following way. So the type of integral we're computing is always of this form. It's always some integral over some space. And then there's some function just called a to the minus s, where s is Mandelstam, and b to the minus t. And then there can be some other function in front that is independent of s and t, or at most polynomial in s and t. So that's the type of integral you want to do. And the observation is just that if you take s very large and also t very large, and the ratio fixed, and the ratio is related to this scattering angle, then you can do saddle point approximation of this integral. So let me recall how saddle point approximation works. It's if you take this very large, then the integral will be very sharply peaked around certain points in moduli space. And around these certain points, you can just approximate the integral by a Gaussian integral. And if you do a Gaussian integral, well, to leading order, you just need to keep, so you sum over all these points where it's sharply peaked. You just need to keep the integrand evaluated at these points, and divide by the fluctuation around these points, which is coming from the Gaussian integral. So it's the square root of the determinant of the Hessian, which is the matrix of second derivatives around these points. And you need to sum over all the saddles, and there can be in principle some multiplicity of these saddles in this approximation. So that's how saddle point approximation works. And you see you can apply it to this problem. And you already see that from this, you will always get some exponential behavior in large energy, because this is something to the minus s. And then there can be like subleading corrections. So this is essentially where this exponential fall off is coming from. Gross-Mende went beyond this, and it told us also what saddles there should be. So they made a proposal for a set of saddles. At tree level, it's easy. At tree level, you just solve where the saddle point equation is. This is the integrand, if you go back to last week, that we computed, that we had for the tree level scattering amplitude, the Mizera-Shapiro amplitude. And you just find some answer. There's one z that is the saddle. And now if you go to high loops, then they identify the set of saddles that can be obtained as a covering of the tree level saddle. Meaning that tree level saddle is a 4-point function on the sphere. So it schematically looks something like this. And now the one loop saddle, for example, is just you take 2 copies of this 4-punctured sphere, and you put in a branch cut here, and you put in a branch cut here. And you can see that this is a torus, because if you go through one of these branch cuts, well, it teleports you up here, then you go around here, and then you get teleported back down, and you can close the contour. So there's a closed contour, which is one of the cycles of the torus. The other cycle is if you go around one of these branch cuts. So that's a particular surface that appears in this integral over tau and the z's that we had before. And Gross and Mende showed that these are saddles. And in particular, if you take these saddles, these are G+1 fold covers of the tree-level saddle. So for genus 1 loop, it's a two-fold cover. And if you look at the saddles, you find that the contribution from the saddle to the string amplitude goes as follows. There's some polynomial piece you don't have to care about. The important thing is this exponential piece. And it goes like exponential of minus s times some function of the angle divided by the loop order plus 1. So one way to think about these saddles is that from a space-time perspective, so these are some special surfaces. And at higher loops, the special surface looks exactly the same as the tree-level surface, except that you superimpose it G+1 many times on itself. So you just take the tree-level saddle and you put it G+1 many times on top of itself. Then you cut open these worldsheets and you connect them in different ways. And so in some sense, you can think of these saddles, it's kind of fake higher loop order, in the sense that usually we think of higher loop order as drawing some nice diagram with many loops in them, but actually all the loops are on top of each other. So it looks like a tree-level saddle. Okay, so that's the prediction that they made, that the amplitude behaves to leading order in this way. And in principle, you can be more diligent and compute also the one loop fluctuation around that. You can turn this into an exact prediction. And so let me just tell you what the consequence, first of all, is. The consequence is that the amplitude roughly looks something like this. So if you take the genus 0 amplitude, it exponentially fast dies off with some given rate. And the genus 1 amplitude also exponentially fast dies off, but with half the rate. Genus 2 with 1/3 the rate, genus 3 with 1/4 the rate, and so on. And so you see that even though at low energies, there's a nice hierarchy of the different loop orders, and perturbative string theory is sort of well defined. If you go to high energies, the loop expansion breaks down essentially completely. And at some given loop order, at some given energy, the amplitude is completely dominated by a given loop order, which might not be the tree level. So for example, in this energy range, it's completely dominated by the one loop amplitude. So that's the rough prediction of Gross-Mende, and you can turn it into an exact prediction. But there are a bunch of challenges with that, and they were not resolved by Gross and Mende. So maybe the biggest one is that the contour that we're integrating over lives actually in this space, this complexified space. So Gross-Mende only searched for saddles in the uncomplexified space, but a priori there could be complex saddles that contribute to this integral. And then you can worry whether they do, and it turns out they do contribute. There are such saddles and they do contribute at the same order. Then you can ask whether there could be even more saddles than the one that Gross-Mende suggested, plus these complex saddles. We didn't find any at genus 1, but the question is open at higher genus. In any case, if you now take the data that we computed, so you take the, let's say this is the imaginary part of the amplitude, again as a function of the energy. Now we pushed up the energy much higher than in the previous plot. And you multiply by the prediction of Gross-Mende, and it goes in this way. So then you expect that this thing is order 1. And then you plot the answer. Well, so this blue thing is our explicit data. It just evaluates this unitarity cut to very high energies. So we can do it up to some like 53 or something. And then for the integer values, we can do it a bit higher. And then you compare to this Gross-Mende answer, and the Gross-Mende answer tells you that this tends to 1. And usually it's not true, because you have all these wide oscillations. But what we can do is we know that there are more saddles. So this Gross-Mende answer just corresponds to picking a particular saddle, but in fact there are more saddles. And now the game that we played is we take all these saddles and we extract the multiplicity of the saddles from this data. So essentially it corresponds to, you see this data has various oscillations on top. So if you take this data and you apply a discrete Fourier transform on this data, you can read off the multiplicities of the different saddles. And if you correctly do this, you get this red curve. So the red curve is the is this gross Mende evaluation. However, you take in also complex saddles, not just the saddle that gross Mende told you about. If you take in all these complex saddles, well, you get the correct answer. Very good. So yes, this is just essentially what I said. So from this numerical data, you can conclusively see that all these complex saddles contribute to the amplitude. In particular, you find that the multiplicity of the gross Mende saddle is something non-trivial. So it's not 1. It looks kind of funny that there's like this trigonometric behavior. The reason is that I resummed already various saddles. So there are many saddles that differ just by overall phases, and you can sum over the different saddles. So we always think of multiplicities as being trigonometric polynomials. On top of this, there are also saddles that have genuinely different Hessians, and they're labeled by some element in some modular group. This is some congruent subgroup of SL2Z. And there you also have to extract all the multiplicities, so there will be some function of this gamma. So in any case, there's some long story, but essentially all these saddle multiplicities can be fixed from applying consistency conditions and comparing to the explicit numerical data. And we make some proposal for the precise high energy behavior of the amplitude. So, and one sort of important thing also that comes out is that the gross Mende answer was purely imaginary. So that's also what I showed you already in the previous plot. So the prediction for the real part, apologies, this should be real part, not imaginary part. The prediction of gross Mende for the real part was that asymptotically it goes to 0 in the high energy limit. But if we compute it, and again normalized by this sort of this naive gross Mende behavior, it does not go to 0. So this is the explicit data, and again for the integer parts we can push this data much higher. And again we can take this data and extract from this data the multiplicities of different saddles, and if you extract all the multiplicity you get this red line. And you see it does not go to 0. It's essentially on the same footing as the imaginary part. All right, any questions?
Why does it get better? Well, okay. To the left, lower energies, the numerics and your resum saddles differs a little bit. Out to the right, you only have. Should I read your graph as numerics and analytical result coincides, and you?
Yeah.
If I look to the right, to the left, it doesn't quite, right?
Yeah, right. So first, good question. So I didn't explain it maybe carefully enough. So what we did is everything that's blue is the explicit numerical data, and it breaks off somewhere. So
Okay.
this is at 11. So because this is essentially, so if I go back, I told you that this is roughly, we can go up to some range, and the computing the full real part is essentially the hardest thing you can do. So this is why we are sort of only can go up to some order 10 thing. We can go higher up if you go to only integer values. So there are some technical simplifications that allow us to push this higher.
Okay.
So we know also these data points. Whereas the red thing is the answer from the saddle point evaluation. And it should asymptotically match the answer that you get from this blue curve and the blue points if you go all the way to infinity. So here the matching admittedly doesn't look great. And
Also not catastrophic.
also not catastrophic, yes, but it should also not be perfect because it should only be perfect over here. So for the imaginary part, you see the matching is essentially perfect because we're way further over here. But for the real part, we only have data up to roughly here. It's much harder. So there also the matching wouldn't be perfect if I extend the red curve all the way over here. Yeah, so for the real part, we have less confidence than for the imaginary part. For the imaginary part, we're pretty sure about things. So whenever we extract one of these multiplicities, we get some answer, some numerical answer. And of course, multiplicities have to be integer. So for the imaginary part, it happens that multiplicities come out as 3.001, and then we're pretty sure that the answer is 3, something like this. For the real part, they come out as 3.1, so you're less sure that there are 3. But so our conjecture for this asymptotic behavior for the real part is a little bit less strong than for the imaginary part. But we think this is the correct answer, even though here it doesn't look great, admittedly. All right. Any other questions? Otherwise, I think I'm essentially done. So let me just summarize, and then maybe there are other questions. So the main message was that contour deformation methods are powerful to compute integrals that appear in string theory. So you can use them to give exact evaluation of string theory observables. So the one that I cared about in this talk was the one loop amplitude of 2-to-2 scattering, graviton scattering. You can apply it in principle to different observables. And these techniques are numerically useful in the sense that you can actually get numbers out of the amplitudes. And this is pretty hard to do if you just have the integral representation. And sort of the slogan is that you can do the integral without doing the integral because you just deform the contour in some way that makes it sensitive to the integrand near these cusps in moduli space. And then you can always compute the integral near this cusp in closed form. And so you turn integrals into infinite sums. And typically these infinite sums make all of the analytic structure manifest in the amplitude. That's why you don't expect some kind of divergences or so to happen in these infinite sums. And finally, I showed you that we can make contact with this gross Mende limit, this high energy limit, but there was a surprise that actually the high energy limit looks much more complicated than what was envisioned by Gross and Mende. So it's not dominated by a single saddle, but by many, in fact, infinitely many saddles. And they lead to a very intricate oscillatory behavior in the high energy limit. And maybe if I go back to this picture, you see that this was a very schematic picture, but on top of this, you get now many oscillations. And so you can really try to follow the amplitude to very high energies. And in principle, these oscillations correspond all to very complicated resonances that you have in the amplitude. So you see more and more complicated resonances as you go to high energies. And ultimately, you think that these resonances are, in fact, the black hole microstates that you can see in the amplitude. So that's sort of the future dream at some point to make this precise. So thank you very much.
So are there any questions in the room right now?
Yeah.
No?
Maybe a question I should have asked earlier. Just to sort of check that I understand. So we are initially we're integrating over modular space, but we say actually we need a complexified modular space.
Mm-hmm.
And then pick contours that are Lorentzian. How do we do that in a sense? How do we know that we're correct in the contour that we pick?
Yeah, good question. So let me go back to this part. So how do we know what the contour has to do? And essentially the philosophy is that so you integrate over all shapes of the surfaces. And if the shape is sort of generic in the sense that there's nothing that becomes long, so no cylinder that becomes very long, then there's no danger in this integral. So the integral is fully convergent and so on. You are sort of deep into string theory regime. Whereas if you go, so all this I epsilon prescription is an IR effect, right? It's implementing the causality at low energies. So whenever you go to the boundary of moduli space, then there's some piece of the integral that becomes very long. There's like a very long cylinder developing in the worldsheet. This is to your previous questions. How do these stringy amplitude reduces to field theory amplitudes? So there's a very long piece developing, and then you know what to do because it's just field theory. In field theory, you know exactly how you implement the epsilon prescription. Well, you take the Schwinger parameter, and the Schwinger parameter in the way that we drew it in the beginning. I have one formula here. I wasn't very careful last time whether this is a Euclidean Schwinger parameter or Lorentzian Schwinger parameter, in the sense that whether it's the Euclidean length of this internal line or the Lorentzian length. So in principle, it should be the Lorentzian length, right? We have a Minkowski metric on this word line also. And that tells you that to go from the Euclidean Schwinger parameter to the Lorentzian one, you have to multiply this with I. And whenever you multiply it with I, you go into the complex plane and you do this this kind of picture that whenever before you hit the boundary of the moduli space, so then there's a long cylinder developing, you go and you do this Wick rotation. So the answer essentially to your question is that whenever so this is an IR effect. The IR, it reduces to field theory, and then field theory, you know what to do.
Okay.
That's the short summary. So maybe I should also emphasize again, string theory has no UV divergences. It has many IR divergences, but these are physical effects like onset poles, thresholds, and so on that you do want to be there. And so you have to, every IR singularity that you know in QFT will appear, and you have to properly deal with it. And it always appears at the boundaries of modular space. It's because you're doing an integral over a non-compact region, and this starts to diverge, and it diverges from very long lengths. So it's always an IR effect. But you always know what to do because it's just the same as in field theory.
Okay, thank you.
Okay, you did your calculation at a fixed T over S. Any large S but fixed T over S. Anything interesting happening in at different angles? Any clear things you can say without? I mean, I guess you presented results at a fixed T over S because well, the numerics is probably costly enough, so you do it in a spot where it behaves reasonably nicely, or
yeah. Okay. I can give maybe some answers to this. So yeah. So here I did some. So you should read 60 degrees essentially as a random angle. We did various different angles, so we didn't do like a full 2D sweep of angles. So what? Yeah. So there's one thing that happens is that this exponential fall off. So first of all, there's this function f of theta that we do know what it is. So it is biggest at 90 degrees. So at 90 degrees it falls off the fastest. This is why we, for most of these plots, it approaches the asymptotic regime the fastest for 90 degrees. That's why we mostly took 90 degrees. And you also see that here there's still some periodicity. So you see that this has some period of order 4 in the plot, which is it's a special feature of 90 degrees. Essentially, the period, whenever S over T is some rational number, you will get some period that is like the least common multiple of the fraction of S and T or something like that. So in this case, because T is minus S over 2, you can still get some period. If you look at some random angle, truly random, then this plot will just look completely chaotic to you because there are different frequencies superimposed, and they don't have any shared common period, so it will just look essentially random. So yeah, that looks irregular. It's maybe a bit misleading. Yeah, so I don't know whether you had in mind any other question. Well, one thing I can maybe also say is that often it's speculated that if you take high energy limit of a string amplitude, it should look chaotic because it reduces to expected to make contact with black hole physics. This is not correct at all, I think. At any fixed loop order, it's still some versatilles. It's not chaotic in any way. I can write down the result in closed form. And this makes a lot of sense to me because if you're at any given loop order, well, you can look at the high energy limit of this one loop of any given loop order, but it will always, you cannot go to very high energies in the sense that it will always be subleading to the next loop order there. So at every given loop order, the answer does not look chaotic, but it becomes more and more complicated if you go to higher and higher loops. So eventually, I think it makes sense that if you look at the non-perturbative amplitude and you go to high energy, then it looks sort of chaotic.
It's not that fixed. Yeah, okay.
That was not your question, I think that.
That sounds.
Yeah.
That's pretty reasonable. Mine is pretty okay.
All right. I also had one question about something you said at the end, because I was just thinking about what do the oscillations mean physically? You were saying they might correspond to black hole microstates. Could you maybe elaborate a bit on the physical interpretation of how your result differs from the Mende result, and what the oscillations mean?
So in general, whenever you have some bump in the scattering amplitude, then it corresponds to some resonance, right? It corresponds to having some pole in the amplitude that is maybe not exactly on the real axis, but is slightly shifted in the complex plane. So meaning that you have some resonance that has some decay with and decays again. So for example, if you do this in QCD, you see various bumps. Those bumps can correspond to like various bound things of quarks. Should be careful with this because I know that people in the audience know much more about QCD than me, but you can see various resonance of quarks and glue balls and things like that in principle. So here it's expected to be similar, that if you have various bumps, then they correspond to various bound states. And if you add still energies that are somewhere here at any given loop order, you expect that these resonances that you have correspond to something like string balls. So these are like objects that are bound together, but they're still loosely bound. It's not that they're black holes. They are still some like ordinary matter in some sense. But there are some stable resonances and they have some decay width. If you truly go to higher and higher energies, you still see many of these resonances and becomes more and more chaotic where they are located. And you see more of these resonances. And then at this, if you cross the Planck energy is in these units is still like sort of arbitrarily high up because the Planck energy is at weak string coupling is much bigger than the string scale. So if you're at weak string coupling, you have to go to very high energies to see the Planck scale. So if you cross the Planck scale, you expect that slowly these string balls merge into black holes. And then you see certain excited states of these black holes. All of them are unstable because there's Hawking radiation. They will decay again. So these are very small black holes, not the large black holes you have in our universe. Yeah, but you expect that all these bumps are some excited states of these black holes.
All right, thanks. That
Yeah.
answers my question. So the only one person online is Will. I'm not sure if Will still has a question.
No real questions, but just as a comment as a QCD practitioner, the discrepancy that was so disturbing to you between the IR analytics and numerics was something that we would be delighted to see a discrepancy of only that much in QCD. So don't feel any need to shy away from those results. They look beautiful. Thank you for the great talk.
Thank you.
Yeah, so then if there aren't any questions, let's thank people one at a time.
Yeah, sure.
Thanks, Lorenz.
Yeah, thank you.